So today we'll start talking about dividing devices as a method for particulate removal. Dividing devices divide the flow into smaller parts where they can collect the particles. There are two basic types of collecting devices: filters and scrubbers. Today we're focusing on filters. And then within filters, there are surface filters and depth filters. So surface filters, common surface filter, the coffer filter that you may have in your home. Can be a furnace filter, the lint filter on a clothes dryer, a mask. Depth filters include cigarette filters where the entire depth of that filter is used for removal of particulate matter. In water treatment, they're granular media filters, so sand filter, anthracite filter, where the entire filter bed is used for filtration, removal of particles. We'll talk about scrubbers in the next lecture. Surface filters can be constructed of multiple types of material. These include fiberglass, paper, fabric, can even be ceramic materials, as long as there is pore space through which the media, in this case gases, can flow. These can be applied, as we mentioned, at home, coffee filters, home filter, furnace filter, or on an industrial scale.
So there are high efficiency particulate filters. These are often made from fiberglass. They are designed to be 99.9% efficient for a 0.1 micron sized particle. You may have seen a lot more of discussion about these type of filters. They're being used or promoted for use in schools, for instance, to control aerosol levels in rooms, especially in terms of COVID. They can also be used for removing radioactive material, toxic particles, and microorganisms, as I've just mentioned. Ultra high efficiency air filters are what is referred to as 6-9 removal. So you can see there's 6 nines. So 99.9999% efficient for that 0.1 micron sized particle. And these are typically used in environments such as a hospital, where it's extremely important to ensure that the air is filtered. They also can be used in some industrial facilities where it's extremely important to have high quality air. Now, what we're going to focus on today are these large industrial filters. These have efficiencies somewhere between 99 to 99.9% efficiency. Typically, you're looking at about 99% though, removal at a 0.5 micron size particle. And if you remember, we said that gravity settling and centrifugal settling were not effective at removing particles that size. We can use electrostatic precipitators, or we can use these, filtration units, we'll talk about them later, as Baghouse filters. And these can remove particles down to about 0.01 microns. Now, they also can handle extremely variable dust loadings from about 0.23 grams per cubic meter up to 23. So that's about 2 orders of magnitude changes in dust loading. The materials that are used are very much dependent on the type of gas that you're treating, or really the type of particles in that air, and also the temperature of the airstream. So for instance, if the temperatures are less than 100 degrees C, you can use materials such as cotton, polypropylene, nylon, or wool. If the temperature is greater than that, then there's a significant concern about the flammability of these materials, so they're not used at temperatures in excess of 100 degrees C. When temperatures greater than 100 degrees, to about 250 degrees, you can use materials like polyester, Teflon. Higher temperatures, you're looking at polyamide or fiberglass. You can also look at ceramic materials, and these can be produced in a way that they are sufficiently porous to be used. The biggest concern is that as we move to materials that are more temperature resistant, your cost is going to increase. So there's a significant issue in terms of cost. So the choice of fabric really depends on, we'll see this with the type of collector that you're using, the cost of the media, what is affordable for that particular operation. You can imagine it's very different in terms of the type of material that you would use for creating a disposable furnace filter versus the type of material that you would be using in what we will look at these very large baghouse filters, where the fabric that's used is reused for significant period of time, up to 5 or so years. Longer if it's ceramic, though. And then the other issue has to do with the operating temperature. Again, as we just mentioned, there's some materials you cannot use at higher temperatures. The other issue is how corrosive is the gas? How abrasive is it? Are you dealing with a combustible gas? That will impact what you use. And also, what is the moisture content? And there's some play in terms of the temperature. You can operate at lower temperatures, but then you have the potential for condensation on your fabric, and that can result in corrosion of that fabric material. And deterioration results in potential holes in the fabric, which means that they don't work very well. When we look at the mechanisms of removal, they range from what is referred to as inertial impact, direct interception, diffusion, and electrostatic attraction. What isn't included in here is also sieving. Sieving means that the particle that you're removing is larger than the pore size. Think of that in terms of you're draining pasta and you're using a sieve or a colander for that. Pasta doesn't flow through because it's larger than the holes in the sieve or the colander. What I'm going to do here is play a video. This actually pertains to masks. The video here really pertains to masks, but the removal mechanisms are the same, whether it's a mask or what we refer to as these baghouse filters. So I'm going to play this video because I think it illustrates better these mechanisms of inertial impact and interception, etc. And then happy to answer any questions. So I'll just play this.
Tempting to think of the filter material that respirators and face masks are made of as a microscopically fine sieve that physically blocks small particles from entering your mouth and nose. Unfortunately, the science isn't quite this simple though. The materials that commercial respirators and face masks are made of usually consist of tangled mats of fine fibers. These create convoluted pathways that the air you inhale has to pass through, along with any particles and droplets being carried along by it. For particles big enough to be seen by the naked eye, these fibrous mats actually do behave a little like a sieve by physically blocking them from getting through, but this is pretty much where the comparison ends. This is actually good news, as a sieve that was fine enough to physically block the particles that you can't easily see, and the ones that are often the most dangerous, would be near impossible to breathe through. For many of these particles, it's their inability to follow the convoluted pathways through the filter material that leads to them being captured. To get a handle on this, imagine a car speeding along a winding road. The car fits easily on the road, but if it's going too fast, it won't be able to navigate the bends, and you just know that at some point it's going to crash. It's the same for small particles speeding through a filter. As the air twists and turns, the particles can't keep up, and ultimately they end up crashing out and being caught. Because of their inertia, which, just like the car, depends on how massive they are and how fast they're going, they can't stay the course. But how about the smallest, lightest particles, those that can easily slip along the winding path the air takes? Amazingly, these are also captured efficiently by a well-designed filter material, but the way they're captured is very different. Because really small particles have so little mass, they dance around as they're bombarded by the air molecules surrounding them. And as they dance, they end up colliding with and being captured by the material the respirator or face mask is made of. Because of the way diffusion-based capture like this works, the finer the fibers are that the material is made of, the more effective they are at collecting these fine particles. So much so that some filter materials are made of a web of incredibly thin fibers that are held in place by a mat of much coarser ones. And then you have the middle-sized particles, the ones that are too small to be captured because of their inertia, but too large to be captured through diffusion. These particles are usually a little smaller than 1/100th the width of a human hair, and they are the hardest to remove. This is why respirator and face mask manufacturers test the efficiency of their products with particles in this size range, those particles that are just the right size to slip through and make it to the other side. In a well-designed respirator or face mask, layers of non-woven materials create sufficiently convoluted pathways that the vast majority of these middle-sized particles are removed from the air. But for a respirator or face mask to be effective, it also needs to allow the user to breathe freely. Pack the fibers too tightly and not enough air can flow. On the other hand, pack them too loosely and most of the particles just pass straight through. To make matters worse, because airflow follows the path of least resistance, the smallest hole or gap in a respirator or face mask can lead to it losing most of its effectiveness. This is why it's so important to have a good seal between a respirator or face mask and your face. It's also why wearing one if you have facial hair is not that effective, as it's impossible to get a good seal. This tendency for air to take the path of least resistance also means that some materials are much better than others at filtering out particles from the air. For instance, woven materials are not that good at it. The individual fibers within the threads are far too tightly packed together to allow air to flow between them. And the holes between the threads mean that a single sheet of woven textile quite literally does leak like a sieve. Of course, it's possible to create makeshift face masks with woven materials, but they tend to be somewhat inefficient. Unless that is, you use multiple layers of material, or you combine woven materials with an unwoven one like felt or even disposable floor dusters. The bottom line is that effective respirators and face masks work, not because they act like sieves, but because they use the physics of airborne particles to capture them while allowing the wearer to breathe freely. That is, as long as they don't leak. For more information, please do check out the links in the blurb below, and as always...
So that just gives you a sense of, one, how masks work, and been a lot of debate over the last year about what fabrics you use, whether they should be layered, how many layers. But notice there were a number of statements about being able to breathe through those filter, through the mask. The same is true for commercial industrial systems. It's not breathing, but it's the pressure drop. And it's really the pressure drop across that fabric that makes it difficult to breathe. So if that fabric is too tight, then you've got a very large pressure drop across that filter, and therefore it is difficult to breathe. Same thing is true in these industrial systems, except they're not breathing, but the greater the pressure drop, the more energy you need to supply in order to get that gas to flow across that filter material. The same thing is true, they mentioned, with leaks. So the same thing is true in an industrial system. Leaks are a nemesis of these systems. If you have a leak, it's the path of least resistance, and the flow is going to move preferentially through that hole, whether it's a pinhole or a seal that's improperly placed, but that's where the air is going to flow, and you're not going to get decent filtration. And same is true with a mask. That's why if you watch people with masks, going to do this on TV now, and you look at, it's like, okay, you've got, the mask isn't tight along the edges. Well, that just means that air flows preferentially through those areas, which means that you're not getting the filtration either in or out. And that's a potential risk. Any questions about this? Just that the video explains it quite well, and it's, I think, easier to see than if I actually just try and explain it. The other thing that isn't mentioned in this video is how do the particles stay there? Because your filter material is only as good as its ability to retain those particles. If they're held there for a period of time, but then they dislodge and they can move through the filter, they're ineffective. So what's holding these particles on the filter? Especially true with these really small particles. What's keeping them there? Because remember, the particles are smaller than the mesh size of these filters, the filter material. So when I take a balloon and I rub a balloon on my hair, and it causes the hair to stand straight up on end, what causes that? Static electricity. Basically the same thing. Okay, it's electrostatic forces that hold those particles on the filter itself. It keeps them there until at some point when in an industrial system you clean that filter and dislodge that material.
Tempting to
When we talk about efficiency, the definition for efficiency is much simpler than the equation really, than what we have used for some of these other systems. The efficiency of removal is simply the mass collected divided by the mass applied. So M is the mass collected, C is the concentration, V sub S is our filtration velocity. It's also referred to as the air to cloth ratio. It's referred to as an approach velocity, a superficial velocity. It is simply Q divided by the cross-sectional area of your filter material. And T is equal to time. So we have simply a mass collected over mass applied. And we will use this in an example problem. The average filtration velocity, or this air to cloth ratio, is about 0.01 meters per second, or meters cubed per meter second per meter squared. It can be as high as 0.2. It depends very much on your particle size. It also depends on the material that you are using. And then your efficiency is very much dependent on any leaks, any pinholes that you have in the system. So here is a table of air to cloth ratios. These are for Baghouse filters. As you can see, it's a shaker or reverse. And you see that it gives you values for air per woven material, and then for the pulse jet, it's per felt type material, and it gives you these values for a whole variety of types of materials. Another term that is used extensively is permeability. And permeability is a property of the bed or the filter media, and it's determined experimentally. We typically talk about a clean filter permeability, and we'll talk about a maximum operational permeability. You can also talk about a dirty bed, basically, permeability. So V sub S is your approach velocity. Delta X is the thickness of what we refer to as a filter cake. So we have fluid flow, so the gas stream flows across the filter media. The particles are caught on one side of the filter, so on the dirty side of the filter, and they're going to build up. So what we form is what is referred to as a filter cake. And it's going to increase in thickness as a function of time or as a function of dust loading onto the filter. At some point, the pressure drop becomes so great that we can no longer get gas to flow through. So we actually, at that point, would shut off the filter and then clean it. The other thing to recognize is that the filter actually initially becomes more efficient as that filter cake builds up. So that filter cake is providing some ability to remove particles. So you'll see that generally a somewhat of an increase in the efficiency. Mu is the viscosity of your gas. And then delta P is the pressure drop across this filter. And it will include, for a dirty filter, it will include the pressure drop across the filter cake. So pressure, when we operate these systems, we're operating either at constant flow or constant pressure. So if we operate at constant flow, then the pressure is increasing as the filter is operating. Or if we operate at constant pressure, then the flow rate decreases. Typically, these are operated at constant flow rate so that the pressure is increasing during the operational time. And then when that pressure is too high, then we would shut the system down and clean the filters. So I mentioned Baghouse filters a number of times. These are typical Baghouse filters using a bag similar to a vacuum bag, except these are much, much larger. These can be up to 40 foot long. They can be somewhere between 5 and 14 inches in diameter. And they often have multiple Baghouse filters. This is one from a large foundry, just to give you a size. It can remove 16 tons of particulate matter, 16 tons of particulate matter per hour. It has 16 compartments, a total of 4,000 bags, and each bag is 7.64 inches in diameter and 22.5 feet long. So just to give you a sense of the size of these, they require a large, said that electrostatic precipitators also require a large footprint, so do Baghouse filters. So in order to get the removal that we need a very large system. So we'll do an example here. We have a Baghouse on a nuclear power station. It's a nuclear power station. It is 6 compartments, each with 112 bags. Each bag is 8 inches in diameter, 22 feet long, with an active area of 46 square feet per bag. The gas being cleaned has a flow rate of 86,240 cubic feet per minute. The pressure drop through the freshly cleaned filter is 0.5 inches of water, and will operate the Baghouse filter until the pressure drop is 3 inches of water. At that point, they're taken out of service and they're cleaned. The cleaning frequency is once per hour. And the incoming gas has a particle loading of 13 grains per cubic foot. There are approximately 16 grains in 1 gram, and about 440 grams equals 1 ounce. Okay, so 1 grain is about 65 milligrams, just to give you a sense of what these are. The filter cake is 50% solids, with the balance being voids. The density of the particles is 125 pound mass per cubic foot, and you're asked to estimate the thickness of the cake when the bags are taken out of service, and we'll assume that at any point in time, 1 bag is out of service. So while we have 6 compartments, we'll operate with 5 at any point in time. And the temperature is 150 of the gas is 150 degrees C or 302 degrees Fahrenheit. So I've added just all of the various parameters. We have a lot of information here. So we have 6 compartments, but remember what we said is that 5 are operational at any one time. So the first thing we need to do is calculate the approach velocity, and the flow rate is 60,240 cubic feet per minute. So we have 5 filters operational. I said the temperature was 150 degrees C. So I'll just add that here. So there are 5 filters operational at any point in time. Each has 112 bags, and each bag has 46 square feet of area, and that is 3.35 feet per minute. And I'll just do the conversion. That is 1.02 meters per minute. Okay, so that's our approach velocity. Note the interstitial velocity is always much greater than the approach velocity. Yes, we had 6 compartments, not 5, but we'll assume, actually we were told that 1 was out of service for cleaning at any point in time. So that's why we have 5. Why is the interstitial velocity much greater than the approach velocity? The same is true in groundwater systems with Darcy velocity. So when we look at the fabric, we're looking at this as we've got 46 feet squared. But here's our flow through this. So here's our Q. The issue is that gas can't flow through all of that material, because if we were to look at this microscopically, remember, we've got pore space. So if we would actually measure what is referred to as the interstitial velocity, the velocity through the pores, that would be much greater than the approach velocity, because it doesn't, the approach velocity doesn't take into account the space where your gas can't flow. Now, using the equation for the efficiency, we can rearrange that mass divided by area is equal to concentration times my approach velocity times my efficiency of removal times the time of operation. And we have 13 grains per cubic feet. Okay. We have pound mass per 7,000 grains. So there's 7,000 grains in a pound mass. Our approach velocity is 3.35 foot per minute. We have 60 minutes per hour. We have 0.99 or 99% removal, and we're operating for 1 hour. And that is equal to 0.369 pound mass per foot squared. So mass over that surface area is equal to 0.369 pounds mass per square foot, or 1.8 kilogram per meter squared. And that's meter squared, just to remind you, that's meter squared of fabric. What we're looking for is the thickness, 0.69 pound mass per square foot. We divide that by the density, and the density is 124. Density of the particle is equal to 124.9 pound mass per foot cubed. And I'm going to multiply by 0.5. Why am I multiplying by 0.5? Exactly. It's 50% solid cake. The rest of it is air. Air has a much lower density. I can ignore the density of the air. And that is 0.0059 feet, or 0.071 inches. So the thickness, this is delta X. The thickness of my filter cake is roughly 0.07 of an inch, less than 0.1 of an inch, when I have to shut off the system in order to remove clean that filter. The last thing you're asked for is the permeability. And we said that permeability is equal to V sub S delta X times mu over delta P. And you'll often see a minus there. That's because your pressure is a pressure drop to decrease, and permeability is positive. So this is 3.35 feet per minute and 0.0059 feet. The viscosity is 0.028 centipoise. You need to multiply by 60 seconds, 1 minute per 60 seconds, and then we'll multiply by 2.09 times 10 to the minus 5 pounds force second over foot squared per centipoise. And it's just a conversion there. And then we will divide all of this in the numerator divided by 3 inches of water. And there is 5.202 pound force per foot squared per inch of water. And that is equal to 1.05 times 10 to the minus 11 foot squared. So that gives us the permeability across the dirty filter. So across both the filter and the filter cake. Any questions? So in terms of these filters, so some images of the actual bag in the Baghouse filter. Typically, you're looking at these as having a life of about 1 to 5 years. Ceramic materials would have a longer life, but you're looking at a really big, even larger system. Typically, bags last about 2 years. And diameters mentioned before, but about 0.1 to 0.35 meters on up to about 10 meters in length. So these tend to be quite narrow and very long, as you'll see in some of these pictures. So this is a reverse air system. So the dirty air flows to the inside of the bag, clean air out the side. These can be run what is referred to as continuous offline, which means you pull one compartment offline, you clean those, but you're operating the rest of the unit. You don't have to shut the entire system down. And you clean by reversing the flow. So when you're cleaning the filter, now your clean air in from the outside in, and your dirty air and your particulates would flow then down into a hopper, and you can see that there's a hopper below here. The disadvantage of these is that you can, in the cleaning process, you can get re-entrainment, which means that now you get mixing of this air back in with the clean air, and you're not going to get the efficiency you desire. This is a pulsed jet, and here compressed air is supplied to the Baghouse to operate at pulses. So you're operating pulsed air into the system. You can see these frames. So typically your bag is mounted on this frame mechanism, and these can be continuous offline, or they can be continuous online cleaning. They can be fully automated. Typically here, the particulate matter is collected on the outside. So it's what we refer to as an outside in mode. And so the dirty air is collecting on the outside, and you're pulsing air to dislodge that material. And then you have shaker mechanisms. And here you can see the bag. Here they're hung on a unit. And what is actually done is you operate these either inside out or outside in. You can operate either, but the whole thing is shaken. And that causes the material to dislodge into a hopper, and then it's collected in that way. So different mechanisms, but they all operate the same way with these very long and large bags. The advantage of a baghouse filter, and if you don't mind, I've only got a slide or so, and we can finish this. But the advantages are high collection efficiency. These are extremely efficient, as I mentioned, up to 99.99% efficient. They're very flexible. So you can use different fabrics, you can use different cleaning mechanisms, you can operate these sometimes inside out or outside in. You can operate these over a wide range of flow rates. Remember, with the electrostatic precipitators, we said that changing the operational parameters has a significantly detrimental impact on operation and efficiency. These are very flexible in terms of operation, and that's one of the reasons why they're still used, is because they're so flexible. Pressure drops are reasonable, and they can handle a variety of material. The biggest disadvantage is the footprint. They're large, they contain fabric. That fabric can be flammable, so there's the potential of fires or explosions, and picking the right material, operating at the right temperature, making sure that you don't have explosive gases. You saw this at the beginning, the explosions that can be caused from dust fires or from dust. So you've got now a really high concentration of dust within these units, and you have to make sure that you don't have fires or explosions. And lastly, you can treat hygroscopic materials. So kind of just think about this. If you had a filter like this and it was coated with Jello, trying to remove that off of this filter is extremely difficult. So those hygroscopic materials, that very gelatinous material, is very difficult. So just some misconceptions. The fabric filter bags don't filter. You're actually went through the mechanisms by which they're actually removing. They're not sieving. And the filter cake does provide a significant improvement in the efficiency because it can filter finer particles than the fabric itself. And the bag life is affected predominantly by cleaning efficiency and the energy that's used in cleaning. The more frequent you have to clean, the more energy you have to apply when you're cleaning, the shorter the lifetime of that bag. And these are expensive, as you can see. You can imagine what the cost would be for 6,000. Over cleaning bags is actually worse than under cleaning because of the impact on bag life. So we'll stop there. Sure. Question about filtration velocity and interstitial velocity. Let's just think about this think of this as a sieve, okay? And we have a flow rate through. If we use this as our area and we calculate the superficial velocity or the approach velocity, that's Q over area. But if you want to calculate the actual velocity, how would you do that? So if I want to calculate the actual velocity, think of it as water. It's relative to a point. So let's say each one of these is, let's say it's 1 inch squared. Okay. And I have 9. So the actual velocity or the interstitial velocity is equal to Q divided, I'm just going to say we have 9 times 1 inch squared. So it's the area, the total area of the void space through which the fluid can flow. And the same is true in groundwater, because if this is our groundwater, so here's our soil particles, and I have flow in some portion here, I can use the area across which water is flowing to calculate a Darcy velocity, which is what Q over A. However, the actual velocity is much greater because the water can't flow through particles of geological material, the soil, the particles of sand, gravel, whatever it is. They can only flow through the void space. So the actual velocity is actually going to be much greater than in the case of groundwater. We talk about it as a Darcy velocity. In the case of these systems, we talk about it in terms of a approach velocity. Thank you for asking.